For this lab, I observed a car moving at constant velocity down the road, which means, and according to Newton's second law, that the change in velocity is proportional to the net force on the object, which in this case there would be zero net force, meaning it is moving at a constant velocity. The coordinate system I established had the y direction in the direction of motion of the car, and the x direction was perpendicular to that motion. And then, of course, z was up, but there was no motion in that direction. Here you can see the tracker software that modeled the motion of the car. I placed the y-axis along that white line you can see to the right of the car, and the x-axis, of course, on the horizontal. And I tracked for about 31 positions along that axis for a period of 1.035 seconds. In order to calibrate my object, I used the front right hubcap of the car, which I determined was 0.4 meters in diameter. Also, you can see that this road isn't perfectly straight, and I couldn't get the axis 100% aligned with what I wanted. So there is slight motion in the x direction, but it's negligible compared to the change in y. So that accounts for the discrepancy. For the Python model, I took the initial conditions from the actual car's location on the road and put that into the code, meaning it had the same initial position vector, same final position vector, and same velocity vector as the tracker software indicated. The velocity in this case was determined by taking the displacement between the initial and final position vectors and dividing it by the change in time, which was 1.035 seconds, to give that velocity. That was used in the Python code. I then had the Python code print the time and y position after every loop in the while loop, every time step in the while loop, which I determined should be the total time of the tracker observation divided by the number of frames that I had observed in that period of time. The final results ended up being extremely close. As you can see from the graph, they're basically the same data points, give or take a couple of significant figures. So I would say the model was a pretty good success in predicting the motion of the car when compared to the actual tracker software's observations. Here you can see the graph of the observed and predicted values. They both appear to coincide very closely, which makes sense given the fact that I use the initial position and final position vector as well as the velocity in the Python code to make predictions. So it essentially has the same parameters as the observed value. So basically my only reasoning behind selecting the y-axis as my direction of motion was pretty much because that was the easiest way to do it based on how my video uploaded to Tracker. If I were to switch the axes, the x and y axes, nothing really dramatic would change in the data except that the x and y velocity components would swap. Otherwise, it wouldn't change the motion significantly to change which axis the car was moving along. If it was to move in the positive x direction, it would still have the same magnitude of speed and velocity component that it does now currently. And to answer the other question, yes, it is possible to give the net pushes and pulls on this object. In this case, there is a normal force and a force due to gravity which cancel each other out up and down along the vertical. And then in the direction of motion, there is a force of static friction pointing behind the car and force due to the engine's propulsion pointing forward. And these both are in equilibrium, so there's no net force acting on the car, giving it a constant velocity.